Thank you very much for the introduction. I'm very happy to be here today and to speak about Non-Gaussian continuous variable quantum networks. So as you see, actually, there is the word network in my presentation. And I just want to start by specifying, actually, what is the kind of network that I have in mind. So, of course, when we speak about quantum network, what we have in mind are mainly quantum communication information network. So here, during my talk, I'm going to use a larger, let's say, meaning of network that I motivated more from network theory, in particular complex network theory. And so the idea is that in any case, I have a physical system which I can define nodes and I can define a link, but could be also a kind of graphical representation of my system. So mainly, as I'm going to speak about quantum complex network, I'm going to have nodes that are quantum system and link that are physical interaction or entanglement link. Of course, these networks are very important for communication information protocol. And mainly, I will speak about the kind of network that also you have seen before, that mainly are class state. And but particularly a network, and especially complex network, meaning that I can consider complex shape, will come later on the kind of analysis I will do for Non-Gaussian network. So far so good. So well, I work on the group that deal with multimode optics. So mainly that we use mode of light in our lab, and in particular, the one that I'm going to consider here are different spectral temporal shape. So these are the systems that are to compose my my network, the node of my network. And then, of course, as the talk before, I work in the regime of continuous variable quantum optics. So meaning that if I want to describe the quantum system that I have in lab, I use Wigner function, quadrature measurements, and these are also the variable that I use to build the link, in the sense that the link between the different nodes are given by a connection between these variables. Very good. So I thank Ulrich because he already introduced cluster states before me. So I'm going to speak about continuous variable cluster state that are resource for measurement-based quantum computing. So here, just recalling the expression that we can use for describing this kind of states. And of course, we speak, I mean, you have a graphical representation where nodes are different modes. And then you have links that are a particular kind of gate, which is the CZ gate that are applied in order to create the good entanglement connection. Yeah, so as have been told before, actually, this kind of state can be generated if you have squeezing and then you have kind of this splitter interaction. So if you just take two nodes and you want to create a two-node cluster, you have to put, I mean, just to send squeeze states on a B-splitter. But exactly this state, which is an EPR state, can be generated directly also in parametric process that are in a non-degenerate condition. So where we consider two different output frequency for signal either, and then you just look at the continuous variable component, you can see that you can directly generate this kind of state. So if you want to generalize for larger cases, as has been shown before, you need to consider a linear optic interferometer with many different squeezed inputs. So in particular, you can have a different temporal mode here and just consider a different spatial mode. And then by controlling actually the optics, the optical part, the linear optics, you can generate different kind of cluster. So in our case, at LKB, the strategy that we use is to use multimode, meaning multimodal parametric process that are pumped by femtosecond laser, meaning that you have a full spectrum, namely a comp of different frequency that can undergo to the process. So meaning that we can have exactly the same kind of process in which the generated cluster has been created among different spectral modes that correspond to different spectral modes of femtosecond laser. And in particular, you can consider that in your initial system, you have squeeze mode of light. So you have a particular mode basis in which you have just squeeze modes that are not entangled. And then after a basis change, you can get one possible cluster shape. So the basis change in our case can be directly done by the measurement setup, meaning the multimode homonyme detection that can select particular mode bases depending on the class that you will generate. Or if you want, you can have also a change of the state by changing the spectral shape of the pump. So meaning there's a more nonlinear engineering of the cluster state. So these have been generated in the lab. Actually, we had kind of cluster state that has been demonstrated up to 12 nodes. Which is very nice, especially because we can have any different kind of shape in a very reconfigurable way. Of course, what is interesting, especially for what I'm interested in, is to go beyond regular clustering, also start to try a different complex shape. So before actually cluster state can be generated with a larger number of nodes, so you can have millions of nodes in the experiment that has been shown by Ulrich and in the setup of Furuzawa too. Of course, even if we are mainly interested in reconfiguring the shape, it's very nice to have also larger clustering to go beyond just 12, 13 modes. And for this, we are considering single pass multimode squeezing, in which we can exploit the time being modes, in our case are pulsed time being, and also actually, as we have femtosecond source, again also the frequency mode in order to have a larger space. We have some preliminary results in the lab for it, so we are able to demonstrate single pass squeezing by measuring at each time being different squeeze mode and different spectral shape. Very good. Then I'm going to enter, let's say, the central part of my talk that is more about non-Gaussian classes. So has been told by Ulrich before, actually, non-Gaussianity is needed if you really want to perform quantum computing on this kind of setup. I mean, there is a particular let's say, operation that can be used to bring non-Gaussianity on the multimode cluster state that we have in the lab, that we consider in our group for many years now, which is a mode-dependent photon subtraction by using some frequency generation. So in particular, the idea is that the signal undergo some frequency generation with a gate beam, and every time we see an up-converted photon, some frequency photon, we know that a single photon has been subtracted from the state, and we can arrange the setup in order to get actually subtraction exactly on the mode which is given by the gate. And so what I'm showing here are experimental data that has been taken by my colleague in the lab 1.5 years ago, where you can see that if you enter, you consider the basis in which actually our state as just squid mode of light, and then you select exactly, which in our case the mid-mode gates, you can exactly select one of these modes as a gate, and you get a click while you recover the Wigner function of the state being negative. This can be done also for the other modes, and also this can be done also for a particular node of the cluster. So here, I remember that the cluster is just a linear combination of the modes, so it's a basis change. So if you want, for example, to subtract a photon from a node which is on the square cluster, you have to send as a gate which is a superposition of the mid-mode gates. This is what has been done, and what you recover is that you, at the end, you have non-Gaussian states. So what I'm showing here for the different nodes are just the quadrature distribution that we get in the setup, and the kurtosis that just check actually the non-Gaussianity. So, and here you see that, here in this picture, we can start to see two important points. One is the challenge, which is given by the fact that we have to analyze a four-mode state. So I'm not showing a four-mode Wigner function because it's quite hard to get it from a full tomography. And also the other point is that, well, if you subtract from one particular corner, the mostly affected one is the one on the other side. So you see that there is something that is going on with topology, which is probably, when you have just four nodes cluster, is quite trivial to explain. But if you go larger, and mainly with more non-Gaussian operation, is going to be a little bit harder to detect. So these are the two challenges that I'm just speaking about. So the first is that is merely an experimental challenge. So how to get complete information on the Gaussian state when you go larger and larger. And here, with standard tomography technique, you are very limited with four modes. And then the second one is more a general classification problem in theory of non-Gaussian multimode quantum state when you start to have very large cluster and you start to have many different non-Gaussian operations. So I will start to tackle the first one. And so this is work that has been done in collaboration with the Università degli Studi Roma 3 in Rome. And so maybe the driving force of this work is Valeria Cimini, that she did a lot of work on it. So actually what we decide to do is to use neural network scenario that we use to interrogate actually for discovering if the states that we have, mainly in the lab, but here I'm also speak about simulated state, has a negative or positive linear function. So artificial neural network has already been used to make tomographic analysis of states, so both in DV and in CV. So here we are not really reconstructing all the states. We are really just checking the Non-Gaussian feature of our state. And so here is the setting. So what we have done is to generate any multimode state up to 10 modes, meaning that can be recast in any kind of cluster. You can have any kind of linear combination between the different nodes. And then we can decide to do a manipulation like single photon subtraction or single photon addition on any superposition of nodes and or nothing. And then actually what we do is that we measure these multimode states in a random basis. And then for each mode, we take 1,000 quadrature at 3 different phases. And we repeat it for 1,000 times. And then all this information is fed on a neural network composed by 3 hidden layers. And we just, in the input layer, we recast it in different beams. We have 15 beams for each mode. And then we ask to the network, actually, if the Wigner is negative or not. So it's actually kind of binary classification problem. So this is where cast for neural network. And here are the results that are presented in the paper. So we can see that we have a validation accuracy that go up to 95, 90, or 80% when we consider 3, 5, or 10 modes. And actually, we recently discovered that we can increase even for the 10 modes. We can go up to 95 by editing the binning. And also, we discovered that this can be robust when training tests with different classes of states. And the most important point, if you compare for 3 modes, where we still can have maximal likelihood algorithm that works for reconstruction, that with the few measurements, we get a higher performance for the neural network compared with the MaxLink. So it can really work with few data compared to the standard tomography technique, and it can go up to many different modes. So far so good. Then I'm going to go through the second challenge, which is I remember mainly a theoretical challenge on classification of this kind of non-Gaussian multimode quantum state. So the idea is that when you have a large cluster and then you subtract or you add many photons, well, it's not totally easy to benchmark. So this work has been done in collaboration with Lincoln Carn and Bhuvanesh Sondar at Colorado School of Mines. So Bhuvanesh just moved very recently to Gila. And I want to go a little bit back on the graph cluster state that was defined in the beginning. So this is what in this work what we call the imprinted network. So we start from a cluster state, meaning that we have different model light that we imprint a network of CZ gates. So something that has to be known about cluster state is that, well, you have just one link, but the correlation, Gaussian correlation, go beyond just the first neighboring nodes, but you can go up to the second step. And this is known, and but when you do kind of local operation, you know that you are going to affect, particularly for local property like Wigner negativity or entanglement, just the node itself, and then up to the second step. So this is something that has been tested in our group theoretically, and we have several papers on it. But then the question is, what is going to happen if at first we just go to more complex shape for the initial cluster? And second, what is going on from quantum correlations between all the 2 different nodes? So we recast the problem in a different way. So in the general setting, we start with a graph class structure, which is an imprinted network of scissor gates that can have a complex shape and then go beyond the regular one. And then, well, we look at another kind of network that emerged from this one, which is the network of photon number correlation. So we recast another adjacency matrix for this network. This is defined as correlation between photon. We use two-point correlation of photon number because it's something that in principle can be measured in a quantum optic experiment, and then they contains up to the fourth order moments, meaning that is sensitive to the non-Gaussian character of the state. And actually, we look at this emergent network before subtraction. You see that you have some more link that appearing, and then after photon subtraction, in particular after 10 photon subtraction, you see that actually the shape of this emergent network is totally changed by the photon subtraction. What we have done is to look at statistics, in particular looking at the statistics of network measure that are derived from the complex network theory, which are, for example, the degree, so the distribution of number of link per nodes, or the clustering. So what we get is that the distribution of the degree of this correlation network change, and then, for example, for this particular one, which is Watt-Strogatz network, you have a second bump appearing on the right side. And well, you can ask yourself from where this bump, so which kind of node are affected by this change in degree, and when you can, you can think that they are the closest one. This is true. Actually, what we did is to break up the statistic around given the different distances from the node from which we subtract. And you can see that the node at distance 1 really affect a lot, so are the one that contribute to the second bump, but not all of them. You have a part of them that are not affecting. So if you go closer actually to this first, so you just take the subgraph at distance 1, you see that actually you can separate a different contribution in different groups that correspond to different connectivity with the other node at the same distance. So really, in the subgraph at distance 1, the different connectivity brings different nodes at different degree, meaning a different degree of correlation. So this is, let's say, the main one of the main points of the paper. I cannot explain all the different results. I just want to go briefly to tell that this particular feature explains us because we didn't see too much effect on this photon subtraction when we observe a tree graph, where actually meaning you don't have so many connection when you go at the subgraph at distance 1. And actually what has been interesting is really we see that in complex network structure, you can have different kind of results that depends on the randomness and homogeneity of different number of link. And really the importance of the local structure, let's say the environment around the point from where you subtract photons. And with that, I want to thanks for your attention.